I realize many of you probably don't have these completely done, but let's take a look and see what you have so far. Write an expression for the perimeter. Remember, perimeter is 2 times the length plus 2 times the width. So here, 2 times the length is going to be 5x to the 4th minus 2x squared plus 2 times the width. The width is going to be 2x to the 4th plus 3x. And now we can simplify that expression. Now, if you actually just left it like this, there wouldn't be anything incorrect about it. I did not specify that you needed to simplify or combine what you could, but we're going to go ahead and do it anyway. So again, the first set of parentheses, can I combine the 5x to the 4th minus 2x squared? No, why not? They don't have the same power on the variable, so it's not the same name. So since I can't combine them, I have to look to see if there's anything I can do to the whole set of parentheses. And that's the times 2. 2 times 5x to the 4th, 10x to the 4th. 2 times negative 2x squared, negative 4x squared. My next set of parentheses here, is there anything I can combine inside of them? No. Anything I can do to them? Times the 2. So 2 times 2x to the 4th. It's a positive 4x to the 4th. 2 times 3x, positive 6x. Why didn't any of those powers change? Because there's no variables on the number I'm multiplying. I'm multiplying by a whole number. 2 in both cases, so there's no variable there. I'd have to be multiplying by a variable in order to change the powers at all. Now I'm not done here yet. What can I still combine? 10x to the 4th and 4x to the 4th. 10 and 4 make 14x to the 4th. Why didn't that power change? Because I was adding. When I add or subtract, we keep the same name. So the powers on the variables will never change when we add and subtract. Then this is negative 4x squared and positive 6x. I can't combine those because they have different powers. I can't combine them with addition or subtraction, at least, because they have different powers. So I get that expression. Anybody get that? Anybody sure they would have got there if they had a little more time? Anybody want to run home and cry? All right, well, that's good at least. For the second one, write an expression for the area. Area is length times width, or width times length, however you want to do it. So here what I'm going to do, I'm going to put the width first, the 5x squared, just because it's easier to have that in front of the parentheses, times the length has 2 digits, so I'm going to put it in parentheses. 4x to the 3rd minus 7x. Now what do? In the parentheses, can I combine anything? No, we're subtracting and they have different powers on the variables. Can't combine them. What's next? Multiply 5x squared times 4x to the 3rd is 20. X to the 6th? 5th. There we go. Good. When I multiply, I have to multiply the numbers. 5 times 4 is 20. But when I multiply variables with powers, x squared times x to the 3rd, I add the powers. 2 plus 3 makes 5. 5x squared times negative 7x. Negative 35. 5 times negative 7 is negative 35. X to the 3rd. Good. X squared times x. We think of this as x to the 1. So 2 plus 1 is 3. Any questions on that? How many people had that one right? 1 or 2? I know I cut you kind of short of time. Okay, so our next thing we're going to talk about is just kind of leading into our next topic. And we're going to talk about factoring. What is a factor? A factor is a number that divides evenly into another number without leaving a remainder or a decimal or a fraction. For example, 6 is a factor of 24 because 24 divided by 6 is 4. When we divide it, it gives us a whole number. Or you can, what's that? A factor is a number that divides into that number without and gives you a result of a whole number. So without a decimal or fraction or a remainder. So 6 is a factor of 24 because 24 divided by 6 is 4. It gives us a whole number. Technically, the definition of a factor is a number that can be multiplied by a whole number to give you that. So 6 times 4 gives you 24. Well, they mean the same thing, remember. They're the same operation. One's forward, one's reverse. So there are a number of factors of 24. There are several numbers that can divide 24 without giving us a remainder or a decimal or a fraction. Now, of course, we can divide 24 by 1, but does that do anything to the 24? No, it doesn't. So when we talk about factors, we choose to ignore 1 and the number itself. 24, of course, can be divided by 24 too. But that, again, all that does is give us 1, so it doesn't give us anything productive. So we ignore 1 in itself. What are some other numbers that are going to divide into 24? 2, 3, 4. How about 5? Nope. 6? Yep. 7? 8? Yes. 9? 10? 11? 12? How do I know that 12 is the last one? Yeah, 24 divided by 2, or 24 divided by 12 is 2. There's nothing smaller than 2 that I can use, so that has to be the largest factor, the last factor. How can I, 24 is a number small enough that we can look at it, we can fairly quickly figure out what divides into it. But on larger numbers, there are ways that we can figure out rather quickly if it's divisible by another number. These are called divisibility rules. For example, to tell if a number can be divided by 2, how can we do that quickly? It's even. And by even, we mean the last digit is 0, 2, 4, 6, or 8. So if I have 73,248, is that divisible by 2? Yeah, the last digit's an 8, so yes, it's divisible by 2. How can I tell if something's divisible by 3? Sum of the digits. Let's look at our 73,248. If I add, what's 7 plus 3? 7 plus 3? 10 plus 2? 12 plus 4? 16 plus 8 is 24. Is 24 divisible by 3? Yes, it is. So this number, 73,248, is divisible by 3. Now, if you didn't know if 24 was divisible by 3, the cool thing is, well, 2 plus 4 is 6, and that's divisible by 3. So then 24 is divisible by 3, and then the whole thing has to be divisible by 3. 4. Well, does it really matter if it's divisible by 4? Not really. We can divide by 2 twice, and you'll get rid of 4s. But there is a rule that involves the last 2 digits. So if I'm looking at my 73,248, all I care about are the 4 and the 8. Is 48 divisible by 4? Yes, so 73,248 is divisible by 4. The problem with that divisibility rule is there's not too many people that have their multiples of 4 memorized up to 100. Because that was 92, it might be a little trickier to decide whether it's divisible by 4. Or 84, well, 84 wouldn't be too bad. But you can see that that's not a horribly useful rule. So generally for 4s, I don't worry about it too much. I know I can just divide by 2 twice. How about for 5? Yeah, last digit is 5 or 0. So just taking a peek at it, 73,248, is that divisible by 5? No, it's not ending in a 5 or a 0, so it's not divisible by 5. 6. Now again, I don't usually worry about 6s because you can divide by 2 and then divide by 3 and you've divided out a 6. In fact, that's actually the rule for 6, because you can divide by both 2 and 3. So 73,248, we already said it's divisible by 2 and it's divisible by 3, so it will be divisible by 6. If I have a different number that I haven't already tested, though, something like 81,225. I'm going to give you a little bit of advice here. Always check for the 2 first. I could dive in and start adding digits. 8 plus 1 is 9, plus 2 is 11, plus 2 is 13, plus 5 is 18. Is 18 divisible by 3? Yeah, so that whole thing is divisible by 3. Is it divisible by 2? No, it's not. It's got a 5 on the end. A lot easier to just look at that last digit and see if it's divisible by 2. So I always check that first before I go through the effort to checking if it's divisible by 3. And 3, by both of them. Again, to me the 6s aren't that important because I'll divide by 2 and then divide by 3 and you've got it. 7. Anybody know the rule for dividing by 7? That's good. Neither do I. As far as I know, last time I tried to check, there is no rule for telling if something's divisible by 7. So if one of you guys can go home and figure one out that's going to work every time, bring it in to me. I'll give you an A in the course because I'm going to publish it and probably retire. Hey, you get an A in the course, you got your cut, right? Okay. So there is no rule for 7. 8. This is another one where as the numbers get larger, the rules get to be more and more cumbersome. 8 involves the last 3 digits. So looking at go back to our 73,248. We're looking at the last 3 digits. Is 248 divisible by 8? It is, but how many of you have that memorized so you can just glance at it and see? Apparently you guys have more lives than I do. It is. 248 is divisible by 8. But again, I don't expect you to have memorized the multiples of 8 from 0 to 1,000. It is kind of a fun pastime, though, if you ever get really bored. I'm just kidding. I'm not really that sick, I swear. For 9. Again, 8, it's not all that important because you can divide by 2 3 times. You divide by 2 over and over again, you're going to get rid of anything that's divisible by 8. 9, well, kind of the same thing. You could divide by 3 a couple of times and you've divided out a 9. So it's not that important. But the rule for 9 isn't that bad. It's just like 3. It's the sum of the digits. So our 73,248, if we add the digits, 7 plus 3 is 10, plus 2 is 12, plus 4 is 16, plus 8 is 24. Is 24 divisible by 9? No, it is not. So that is not divisible by 9. At a moment's glance, will that be divisible by 9? Yeah. 7 plus 4 is 11, plus 4 is 15, plus 4 is 19, plus 8 is 27. 27 is divisible by 9. So that whole number is divisible by 9. 10's an easy one. What's the rule? Last digit's a 0. Good. Normally, if I'm looking at numbers to see what they divide by, the first one I look for is 10. Because it's really easy to find. If it ends in a 0, you can divide by 10. And 10's a big number, so it divides it down pretty quickly. Next, I'll look for 5s. In fact, I usually look for 10s and 5s at the same time, because you're looking for a 0 or a 5. After I've checked for 5s, I'll check for 2s, because 2s are pretty easy to check for. You're still just looking at that last digit. If none of those 3 will work, then I look at 3s. I add up the digits and see if they're divisible by 3. Those are about the only ones I ever really check for. The other ones, like I said, 4s, 8s, they all divide, 9s, they all divide out on their own with the 3s and the 2s. There are rules as we go up for larger numbers. Now, like 12s don't matter. You can divide by 2s and 3s. 15s, you can divide by 3s and 5s. So there's something called prime and composite numbers. A composite number is made up of other numbers. For example, 10 is composite because it can be made up of 2 times 5. 24 is composite because it can be made up of a lot of different ones. It can be 3 times 8, 4 times 6, 2 times 12. Then there's prime numbers. Prime numbers are not made up of any smaller pieces. Like 11, there's nothing I can multiply together to make 11, except for 11 and 1. 17 is prime. There's nothing I can multiply together to make 17. 2, 3, 5, 7, those are all prime. There are no smaller numbers I can multiply together to make it. The reason I bring this up is as I get larger, those composite numbers don't need a divisibility rule because, as I said, 12 is made up of smaller numbers, so you can just divide by those smaller numbers. 15 is made up of smaller numbers, you can just divide by those smaller numbers. The only numbers that need divisibility rules are the prime numbers. The only problem is as we get larger than 10, those divisibility rules get very, very complicated. For example, I'm going to show you the rule for 11. You don't need to write this down because I'll never make you do it because it is kind of ugly. So let's go 7,283,540. Oh, let's see what I got here. Oh, well, we'll do that. To check to see if something's divisible by 11, I start with the first digit, and I take every other digit. 7, 8, 5, and 8. 7 plus 8 is 15, plus 5 is 20, plus 8 is 28. Then I take the remaining digits and add them together. 2 plus 3 is 5, plus 4 is 9. And then I subtract. The difference here is 19. If that difference is either 0 or divisible by 11, then the whole number is divisible by 11. So this is not divisible by 11. However, don't know why there's an extra comma there. This number here, 7 plus 8 is 15, plus 5 is 20, plus 8 is still 28. 6 plus 7 is 13, plus 4 is 17. The difference is 11. That number is divisible by 11. Any questions? Okay. There are ones as we go larger, but you can see they get really complicated, and I'm not going to, I mean, the 11, I only remember it so I can show students. I would even have to look up the rule for 13 anymore because it was complicated enough that I didn't pay attention to it. So again, we're looking at these so that we can do factoring. Now we said 24 has several factor pairs. 24 could be 2 times 12, be 3 times 8, or it could be 4 times 6. If I ask you to factor 24, though, which one of those am I looking for? Well, we don't know. So normally we do something, rather than just doing factor pairs, we do a process called prime factoring. Prime factoring breaks a number down into its smallest possible components. So if I ask you to prime factor 24, the process that usually works best for this is a factor tree. We take 24. What is any number that divides into 24? What did you say? 3? Perfect. 3 will work. 24 divided by 3 is 8. So there's 8 left over. 3 times 8 makes 24. Is 8 prime? Or sorry, is 3 prime? Yeah, 3 is prime, so I'm going to circle it. I'm done with that one. Is 8 prime? No, it can be divided into 2 times 4. The 2 is prime. 4 can be split into 2 times 2. Those are now primes. I circle them. Once everything at the bottom of my branches is circled, I know I'm done. 24, I have 1, 2, 3 2's. So 2 times 2 times 2 times 3. That's my prime factoring. You can leave it like that. That's perfectly acceptable. And sometimes it's easier to have it in that form. Or, get rid of this powers, 2 to the third times 3. Either one of those works. So I'm asking the prime factor 60 for me. See what you come up with. What'd you get? Perfect. 2 times 2 times 3 times 5. I would see the 0 first and probably do 10 times 6. If you did 2 times 30, that works. 6 times 10, 4 times 15. Anything that divides into 60 will work. The 10 can be split up into 2 times 5. They're both prime. 6 splits up into 2 times 3. They're both prime. And we want to put them in order from smallest to largest. So 2 times 2 times 3 times 5. Or you could have 2 squared times 3 times 5. Either one is acceptable. My math lab may ask you to put them in power notation. That would be like this. Or exponential notation would be like that. What if I have 45x to the third, y to the second that I want to factor, prime factor. Well, I have to factor the number first. What's anything that divides into 45? 5. Good. 5 times 9. 5 is prime. I'm done with it. How about the 9? 3 times 3. Both of those are prime. So 45 is 3 times 3 times 5. X to the third is x times x times x. Y squared is y times y. So this is written out as individual factors. If I wanted to put it in that power form or exponential form, it'd be 3 squared times 5 times x to the third times y squared. Either one of those is acceptable. Why do we care about factoring? Well, because the next thing we're going to learn about uses factoring a lot. Three-fourths is a fraction. Remember, we said way back on our first night of class that this is a single number with two parts. The 3, the numerator, is a count. It tells us how much we have. We have 3 of something here. The 4 is a name. Just like inches or cows or pounds, that's what we have. We have 3 of those. We have 3/4. So to start working with fractions, we need to first define what does it mean to be a fourth. Well, the simplest way to go about it is to look at the old elementary school illustration of a pie or a pizza. Pretend that's a circle. And fourth means it's cut into 4 equal pieces. So pretend those are equal pieces. So the fourth means a whole object is cut into 4 equal pieces. Or another way of looking at it is it takes 4 of those pieces to make one whole object. The 3 then means that we have 3 pieces. Yeah, my coloring is no better than my drawing. So what we talked a little bit about fractions that we couldn't combine because they have different names. Like I believe we used 2/3 plus 1/5. Couldn't be added because they have different names. So the first thing we need to do is be able to rename them, change their names. From this illustration, the simplest way to rename this or change its name, we would take each slice and cut it into equal pieces. So I'm going to cut each slice into 3 equal pieces. Again, you may have to pretend these are equal. So each slice has been cut into 3 equal pieces, approximately. Now, how many pieces does it make to make that whole object? 12. It took 4 of them before, and each of those was cut into 3 equal pieces. 4 times 3 equals 12. In the yellow there, how many pieces do I have? 9. I had 3, and I cut them each into 3, so 3 times 3 is 9. Do I have any more or less than I did before? No. So 9/12 and 3/4 are exactly the same value. The reason that works is because of what I did right here. I multiplied by 3 over 3. And with what we just learned about fractions, this 3 means it takes 3 pieces to make a whole object. And we have 3 of them. In other words, it's 1. And when we multiply by 1, what does it do to the value of a number? Keeps it the same. It does nothing to it. It doesn't change it. So we multiplied by 1, so it doesn't change the value, but it can change the appearance. This is what we call a unity fraction. Not horribly useful to us right now, but when we start talking about measurements, a unity fraction is what we're going to use for our measurement conversions. And we use them for a lot of different things. It can change the appearance of a number, but it keeps its value the same. So now in this one, we just kind of randomly chose to multiply by 3 on top and bottom. Generally, however, we have a target that we have to hit. So we might have 2/5, and we might need to change it into 20ths. So we have to figure out, what do I multiply the 5 by to turn it into a 20? That'd be 4. 5 times 4 is 20. What do I have to do to the 2? Multiply with the same thing. 2 times 4 is 8. Again, 8/20ths has exactly the same value as 2/5. It just appears different. It looks different. Or I might have 5/8 and I want to change it into 40ths. What do I have to do to the 8 to turn it into a 40? Times 5. So what do I have to do to the 5? Also times 5. I have to multiply by the same thing on top and bottom. 5 times 5 is 25. 25/40ths has the same value as 5/8. Now, if I want to go the other direction and change the name to be smaller numbers, I can just reverse this process. Here, I multiplied by 5. I can divide by 5. 25 divided by 5 is 5. 40 divided by 5 is 8. questions? We've already established that those are the same, right? Now, of course, here, we saw what we multiplied by. So we knew what we could divide by. The trick is figuring out what we can divide both numbers by. So that, yes, just like you'd have to multiply both the top and bottom by the same, you have to divide both the numerator and denominator by the same number. Yes. Yes. Yep. 4 and 4, or 5 and 5, 3 and 3. Yep. Can never change. No. So here, for 48 over 60, I have to look at those, and I have to figure out, is there a number that divides into both 48 and 60? Now, there are actually several of them. Which one do you see first? 2. They're both even. So I can divide them both by 2. Now, many of us were taught that you have to find the largest number that divides both of them. It's called the greatest common factor. That's not true. We can divide by anything. Both of them are divisible by 2, so let's divide by 2. 48 divided by 2, 24. 60 divided by 2 is 30. But now we see that they can still be divided by what? 2. They're both even. Divided by 2 again. 24 divided by 2 is 12. 30 divided by 2 is 15. Now what? Both of them can divide by 3. 12 divided by 3 is 4. 15 divided by 3 is 5. Any questions? You could have actually divided by 12 in the beginning. Both of those numbers do divide by 12. 48 divided by 12 is 4. 60 divided by 12 is 5. I just want to show you is you don't have to find that largest number. You can divide by 2 first, 3 first. Eventually, you're going to get there anyway. It just takes a few more steps if you're dividing by smaller numbers. So we can reduce our fractions in that way. The next thing I want to look at is what if we have something like this. 44 over 7. The 7 is saying it takes 7 pieces to make a whole object. We have enough pieces to make a whole object. In fact, we have enough pieces to make several whole objects. How can we figure out how many whole objects we can get out of this? Divide it, yeah. 44 divided by 7. If we divide that out, we get 6.28571429 approximately. What does that tell us? It tells us we can get 6 whole objects out of here, and there's going to be some pieces left over. We need to figure out how many of those pieces are going to be left over. Now, those pieces are still going to be defined as 7s. So they're still going to be defined as 7s. We've got to figure out how many of them there are. To do that, it's going to be basically a division and remainder. 44 divided by 7. 7 goes into 44 6 times, as we saw. 6 times 7 is 42. So we subtract, there's 2 pieces left over. So that's 6 and 2 7s. 6 and 2 7s, like that. So if we have something like now let's do it, 19/4. How many times is 4 going to 19?
4.
Goes in there 4 times. 4 times 4 is 16, so there is 3 left over. So 3/4. So it's 4 and 3/4. Make sense? Okay. We can go the other direction. I might have 7 2/3. This is what we call, by the way, this here is what's called a mixed number. Because we have whole numbers and fractions mixed together. This is what's called an improper fraction. Now, improper implies that there's something wrong with it. There's nothing wrong with it. In fact, there are times when we prefer to have a fraction in that form. But we don't like having the numerator being so much larger than the denominator because it's harder to visualize. It's easier to visualize whole objects with a few pieces left over than it is to visualize a whole bunch of pieces. But as I said, there are going to be times where it's preferable to have it as that improper fraction. So what we're going to do now is we're going to take this mixed number and turn it back into an improper fraction. Get rid of the whole number. What that means is we're going to have to take this whole number here, the 7, and break it into pieces. Well, how many pieces are in each whole object here? 3. The denominator of our fraction tells us how many pieces each object holds. So we take that whole number and we multiply it by our denominator to get 21. What that's saying is we broke that 7 into 21 pieces. Did we have any pieces before? Yeah, we already had 2 pieces. So we add the 21 to that to get 23 thirds. So let's say I have 4 and 3/5. 4 times 5 is 20. So I broke the 4 whole objects into 20 pieces. I already had 3, so 3 plus 20 is 23 over 5. Any questions? So why is it that we were so worried about factoring? Well, let's go back to our 48 over 60. What's that? 23 over 5. 4 times 5 is 20, but then you have to add it to the 3. Go back to reducing our 48 over 60. If I prime factor 48, now I don't have time to do the tree right now, so you're going to have to trust me. You can double check me on your own if you want to. You get 2 times 2 times 2 times 2 times 3. If I prime factor 60, I get 2 times 2 times 3 times 5. Now I want you to go back up here. When we did this, I'm glad you guys chose these numbers. A lot of groups will jump to 6 or 12 right away, but I'm glad you guys chose these. We divided by 2, then we divided by 2, then we divided by 3. What we're really doing is canceling out factors. We divided by 2, divided by 2 again, we divided by 3. We canceled out common factors. What's left? 2 times 2 is 4. Now on bottom we have a 5. Now don't let this next part scare you, because we're going to come back and talk about this more. This one shouldn't be in the assignment for tonight. But what if I then have 12 x to the third over 28 x squared? If I prime factor, 12 is 2 times 2 times 3, x to the third, x, x, x. 28 is 2 times 2 times 7. Again, if you want to do the factor tree and verify that, I'll let you do that on your own. X squared is x and x. And we're going to cancel common factors. 2. What else can we cancel? Another 2. And we can cancel an x and another x. What's left on top is 3 times x, which is 3x. On bottom is just 7. We get 3x over 7. So we can do algebraic, if we can factor, we can reduce algebraic fractions just as easy as we can reduce numerical fractions. Now I'm just showing you this to foreshadow a little bit to what's coming up in the next couple classes. This should not quite be in our homework yet. Speaking of, there is a new quiz that is due tomorrow, Friday, at 11:59 p.m. There's a new homework. It is due for Tuesday. You guys have a wonderful night, great weekend. We'll see you on Tuesday.